in later slides. So Einstein's general theory of relativity was first predicted in 1916, and this theory gave so many predictions. Quite famous ones were describing the perihelion motion of the uh, Mercury and also the deflection of lights, which is known as gravitational lensing. And one of the important consequences of this theory was the existence of gravitational wave, which was discovered again in 1960. Just like Maxwell's equations tells about how matter interacts with light. I'm sorry, I'm seeing some cartoon over here. Please don't use sketches. Anyways, so just like Maxwell's theory tells about how matter interacts with light uh, for systems like let's say gold or silver or anything appearing in the universe in our earth. So that's way in the same way to understand how the heavy objects or celestial objects interact with each other, that is described by Einstein's theory of relativity. So coming to the third slide, we have, so what do we understand by gravitation waves? So these are basically the freely propagating oscillations of gravitation field. Now, from the first slide, we saw that if we try to solve this complicated equation, we will be ending up lots of equations which are partially derivative and coupled together. So we won't be understanding how the wave equations we can formulate from this sort of set of 10 equations. So what do? We under some approximation, we try to linearize this field equation, and in that linearized equation, we obtain a quadrupole formula, which is similar to a dipole formula in our electromagnetism. So this quadrupole formula, if we try to see, reference is given over here. So quadrupole formula is given in this form, where the wave strain is dependent on the dipole moment of given as I mu nu. And what do we understand from this equation? That the strain or the signal basically scales as 1 by r, where r is the distance to the source. Now, in the Newtonian limit, if we try to approximate this equation, we can obtain a simpler equation where phi is the potential of the system and v is the velocity of the source. And if phi Newtonian, if we give as gm over r, so we can obtain the gravitation wave signal as gm over r c square, v square by c square. So to understand what this equation actually means, let's take a physical scenario. So let's consider a dumbbell shaped system where two dumbbells are of 1 turn separated by 1 meter. And suppose if we try to rotate this dumbbell with some 1000 hertz of frequency, so what kind of gravitational wave or the strain signal we will be obtaining from this kind of system? That will be of the order of 10 to the power minus 39. Now, if we look at this number, this is very small. Like if we compare anything which exists in the universe, like from your hair to the largest object to the smallest object, this quantity is very small. So at that time, it was very difficult to actually think about whether it's actually possible to detect these kind of signals from sources which are of the order of solar masses. So this was one of the important problem which people face at that time. But the motivation came from first indirect observation of gravitation waves, which was the discovery of Hudson-Taylor pulsar. Now, before moving on to the Hudson-Taylor pulsar, we'll understand what are pulsars first of all. So pulsars are basically the celestial clocks revolving or rotating at some frequencies. So the first pulsar discovery was made by Jocelyn Bell and Tony Hewish in 1967, which got the breakthrough prize in 2018. Now, we knew that these are the celestial clocks which are existing in our universe. So after the discovery of first pulsar, people started looking for more pulsar systems, whether it can exist as a binary system or individual system. Astronomers started looking for those kind of sources. Then in 1974, Hulse was the graduate student of Taylor. So they discovered this pulsar, which showed some peculiar behavior. Now, what are the peculiar behavior they were showing? This pulsar was showing. So they took a survey for approximately 10 years. And in this survey, they found that the pulsar didn't show the periodicity. And if we talk about pulsars, there is a periodicity in their nature. But this particular system didn't show the periodicity in its in the result. Now, that made some confusion why it should not be showing any periodicity. That means that the system is sort of, the periodicity is sort of like decreasing over time. And this is what later on was proved by Weisberg and Taylor in 2004, that the orbital orbital period of the system was decreasing over the time. Now, this gave an indication: is it the system in a binary system? That was the question which arose at the time. And if we understand that the gravitational wave or the general relativity is correct, then basically any decaying system will eventually should emit gravitational waves and finally spiral inwards and merge together. So this was not a direct but indirect evidence of existence of gravitational wave, which made researchers to look for uh, gravitational waves and their sources. So talking from the pulsars to what kind of sources we can detect for gravitation waves. So this is a plot where you can see the frequency versus strain. And there are many sources out there in the universe, but starting from compact binary coalescence, which has a frequency of 100 to above, and we have somewhere around 10 to the minus 8 of frequency band, which shows all the supernova burst. And going below to the frequency, we have radio pulsars. And if we go to the frequency range, which is very small, then we eventually detect CMB. Now, if we compare the frequency versus the strain plot, what do we see? That by from going left to right, sorry, right to left, we are decreasing also in the frequency, and also we are increasing the strain of the of the signal, gravitational wave signal emitted from these objects. Now, what do we see is that experimentally we can measure the gravitational waves from the objects in this regime. Okay, but this is sort of like still like far away. We still not haven't detected. So out of all these sources, so far the current scenario given, we have only detected the sources from ground-based interferometers, which mostly detect the signals from the merger of compact objects. And this we will see in the next slide. How do we actually see gravitation wave emitted from these objects? Okay, so far we have detected 10 binary black hole mergers. And if we see this gravitation wave graveyard, you can say, we have from the EM neutron star population, we have only detected one
Actually,
confirmed neutron star. Sorry. Yes. So we have detected one neutron star with EM counterpart, and from the population of EM black hole, we have detected almost 11 of them. I'll describe few which are recent one in the later slides, but this is the current scenario where the masses are ranging from 1 to 80 of the solar mass. Okay. Okay, so understanding the frequency time characteristics of gravitational wave from compact binary mergers. Since in the previous slide, I explained that we can only detect the gravitational waves from the merger of compact sources. Now, how these compact sources merge is it can be actually pictured in different phases. So let's assume that the two black holes, when they are in the inspiral phase, the frequency and the amplitude are sort of like constant over here. But when over the time, when they eventually come closer, it emits the radiation, and this frequency versus strain graph shows that it increases in frequency also and in time, and at the end it merges, and we see a ring down part over here. So the overall frequency time characteristic shows a inspiral merger and ring down, forming a characteristic chirpy kind of signal, which we can see in this video over here. So you can see that the two black holes are revolving around each other, and eventually they will merge. But if you look at the gravitational wave polarization over here, it is increasing in time and also frequency. It increasing in amplitude and also frequency, and finally it merges. So this is the characteristic chirpy signal which we try to detect in our through our detectors. Now, what are the ground-based detectors we use for detecting these kind of sources? So we use gravitational wave interferometer system, which you can see from this cartoon. So we have the gravitational wave interferometer looks like this. So we have a laser source, and we have a beam splitter which splits this laser light into two directions, and we have one cavity on the top side, and on the right hand side we have the second cavity. So what happens is that the laser light falls on this beam splitter, and the light gets split up, and then from it gets reflected back, and then we after signal recycling, we detect the injected signal near the photodetector. And to visualize this, okay, I'm sorry, yeah. So here is a small video where you can see how this actually works. So we have a beam splitter where the light gets travels, and then it gets reflected by the mirrors over here. And what do we detect? So we inject the known signal over here of certain frequency, and then when we recollect back, we try to see the interference pattern produced by the change of the arm length. Now, how do we say? Now the system is actually in a stationary phase. But if suppose there is no gravitational wave, so basically whatever injected laser power we have given from the source, we will be detecting at the same power at the end. But what happens if the gravitational wave is present? So as I said, the gravitational waves propagate through the space-time, and it distorts the space-time. It squeezes and it expands the space. So the continuous squeezing and expansion, basically it changes the length of the arm. Now this length of the arm is so tiny, as we calculated previously. It was somewhere around 10 raised to the minus 39. So this small change which we detect it can only be possible through interferometer kind of system. This is what we detect. And talking about what all challenges we face in terms of detecting this small change in the length will be seen in the next slide. Okay. Yes. So talking about gravitational wave detectors noise budget. So we saw that the gravitation wave detector has lots of components attached. Okay, we have laser, we have photodiode, we have mirrors attached, which are basically hanging from a very tiny strings made up of glass. And these are like freely suspended mirrors because we don't want it to interact with any seismic activity which goes on Earth. So this is one of the reason. So we have like lots of components over here, and each component contributes some sort of noise. Okay, so let's see what kind of noise we see from gravitation wave detector, excluding the signal over here. So we have quantum noise appearing. We won't talk about this over here, but let's talk about the seismic noise. Seismic noise basically contributes to the human activities which goes on the Earth. Um, Walking, people walking, or cars moving, all these activities come under seismic noise. And you can see that the seismic noise curve is shown by oranges color over here. And we have other sort of noise, Brownian noise, etc. And then the gas is filled over here, and then what kind of excitation it goes into, and everything. So everything contributes some sort of noise. Now let's add all these noise component noise together. We get a total noise curve, and this is what we have to overcome for detecting any gravitation wave which comes at the level of 10 raised to power minus 21 or 23 or beyond that. Okay, so this is the total noise budget, and this is the sensitivity of the current system. We have blue colored sensitivity for LIGO Hanford, and red one for Livingston, and magenta for Virgo. This I'll explain in next slide. So, but this is the noise budget we have to overcome in order to detect any signal. Okay. Okay. Talking about detectors of gravitation waves. So currently we have four detectors, out of which we use three: LIGO Hanford and Livingston and Virgo, for detecting binary sources. Geo 600 is also working, but then again it has a lower sensitivity. Kagra is one of the detector which is there in Japan, and LIGO India, which will be there after 5 or 6 years from now. So this is the way how LIGO detectors look like. As I showed in cartoon, we have two arms, okay, and we have a beam splitter over here, and freely suspended mirrors which are attached at the uh, ends of these tunnels or the arms, which you can see. And Kagra is sort of like special because it is built under the hilly area you can see over here. That is just to minimize the noises and etc stuff. And but there are other challenges which this particular detector faces. And yeah, so this detector is going to come up in next observation run. Now understanding gravitational wave and detecting them is not just a one person job. There are like hundreds of thousands of members which are working together, and hundreds of institutes uh, spread across the countries which come together, and they work together in order to detect all these signals. So this is like a Virgo Kagra collaboration, which we will be seeing. Okay, so I'll take a break over here if anybody have any questions, because after that there will be the talk will be slightly technical. So if anyone have a question, please go ahead.
So I have a question.
Yes.
So we're dealing with interference pattern here, right?
Yes.
So when there is a fluctuation in the path difference of the both waves, so we would be measuring the shift in the interference pattern, right?
Yes.
So that would be since it is like really small, the shift would be also like really small, right?
Yes.
So that's why it is really difficult.
Yes, it is difficult, as I mentioned in slide 2. So this was okay. Let me go back and give you a feel of number, how what kind of strains we are looking at. So this particular diagram I showed, that if we imagine a physical scenario where we assume two dumbbells, okay, where one ton masses are attached, and if this is 1 meter apart and we rotate this particular system, this will produce a gravitational wave strain, or you can see this number as a change in the arm length. Okay, so this particular number will correspond to somewhere around 10 to the power minus 39, which is very very small. And if you see the LIGO sensitivity, our detector sensitivity here, so this 39 comes somewhere in the bottom. So basically, you need heavy masses in order to detect any kind of sources which is out there, and we have to cross this barrier in order to see any sources out there. So this is the main challenge which people face in detecting gravitational wave sources from celestial objects. Yes.
Question.
Did it answer your question?
Yes, it does. Thank you.
Okay.
I have one question. I have two questions actually.
Yes.
The first one is the diagram which you showed, that strain and frequency diagram. So you limit the left hand side to CMB. So why we can't go before CMB, say inflation and all? So because the Big Bang is supposed to create more strain, and so what is the limitations? That is number one question. Because
No, this is just to give a feel of what all kinds of sources out there. We definitely this is just to see. I was just comparing the number, and I think I made a mistake over here in the power at the bottom. Uh, but apologies for that. So there can be sources. Let's say we assume sources like supermassive black holes or anything. Okay, so these kind of sources, they emit in a frequency range which are much more smaller than any of the sources which I have listed over here.
no,
Okay.
ma'am. No, ma'am. I wanted to ask something else. I want
Yes.
to ask the prior to the CMB. I mean, in the time prior to inflation and all, prior to CMB. So, can the gravitational waves help us in getting information prior to CMB? Because the Big Bang itself is the biggest event. That's
Yes.
what I was asking.
Yes. So that's what, like, okay, it can give information, but we are just limited by the sensitivity of our detectors. We need to have space based or some other projects, or which can reach to the sensitivity level of 10 to the power minus 40 or 50 in order to detect those kinds of signals. So we do have some sort of like background created, like CMB background, sort of, but we are just limited by the sensitivity of our detectors because we have louder events over here, and we
No,
need to.
that's
Uh,
exactly what I was asking.
yes.
Forget about Big Bang. So inflation itself, don't you think that is going to give a bigger source than the latter events, the CMB, or that's exactly the point.
Uh, One has to find out. I mean, that's what I can say. I mean,
Okay, fine. Okay,
yes.
fine. And second question is, does gravitational wave get stressed? Is there any stretching like EM waves?
Yes.
So,
Yes,
so
it
what?
gets reflected. It gets all the sorts of phenomena which you can see in the case of light. Okay, so light gets reflected, it gets squeezes, and then it bends also. So all these phenomena can also be seen. You can even get the gravitation wave modulated just because a source is kept. So suppose you might have heard the phenomena of light getting deflected by a lens. Okay, so these sort of systems, these sort of phenomena can be also seen in the case of gravitation waves, where the frequency can be modulated and changed or amplified even
Actually,
because of
actually,
sources.
actually, ma'am, I can't communicate my question. The
Yes,
question is, like radio waves, which we see stressed, right? I mean, as we receive here because of the expansion of the universe. So, if radio waves can be, I mean, the EM waves can be stressed, can whether gravitational waves are different, can be must have been stressed or not because of the expansion of the universe. What we are detecting right now, is it a stressed one, or it is not affected?
sorry, there was some problem. Can you just repeat? Sorry, there was
Yeah.
my
What I was
screen.
asking, ma'am, is say, let us say any EM wave, or radio wave.
Yes, yes,
So when we are receiving the radio wave, we know it has red shifted because of the stretching, because of the
yes,
expansion of the universe.
yes,
Whether the same principle applies to the gravitational waves,
yes,
what
yes,
we are
it can apply.
receiving is the stressed one with the.
Yes, yes,
That's exactly what.
yes, it can apply. Yes,
Thank you.
yeah.
My question is, if you please go back to the diagram of your LIGO.
Okay, just a minute. Yes,
Here are all the instruments required, in the sense, I have actually two questions about LIGO.
okay.
Question number one is that are all these quite necessary to increase the sensitivity, all these instruments which you've put, except for the beam splitter, the laser, and the uh, two reflectors from where it is reflected, are all the other things necessary? And of course, the photo detector. All the other things which are they necessary?
Yes, actually. So let me give a comparison uh, to our optical detectors. So in the case of optical detectors, we can see the sources and we can take pictures and we can analyze the data. But here in the case, we are actually looking for a signal which can make a length change of the order of 10 raised to power minus 23 or 22. Okay. To this extent, to this small to understand the change in the length of this much number, we need a very high sensitive instrument, and the most sensitive instrument you can build is by interferometers, because here what we are trying to do is we are keeping the arm lengths and everything constant, and we are assuming that if the gravitational wave passes by, it can stretches and squeeze the space around it. Basically it can change the arm lengths to some extent that can be measured from the detectors. So this is I'll explain how the detection actually works in the next slide, but these all components are basically necessary. And I have just shown, I mean, this cartoon represents only few uh, components, but there are like thousands of components will be attached to each of the test mass and etc. In order to increase the sensitivity of the system. Does that answer your question?
Yes, my second question is, do these arms have to be, I mean, separately, individually, each arms, do they have to be 1D from when looked from above, I mean, outer space, or can they be in 2D planes?
2D planes, this is actually placed
No, I'm saying only individual arms. I'm not saying the whole system.
mhm. No, interferometer. Okay, I'm not sure whether you know how interferometer works, but interferometer design in itself is made such a way that we have a beam splitter which splits the light into two, and we record the interference patterns over here. So maybe you can go back and then read about interferometers. That will, I think, answer your question. This is a system. Any other question?
Thank you.
Shall I move ahead? Okay, if there is no question, I'll move ahead with my talk. So, second part of the talk is a bit technical, so bear with me. There will be a lot of equations and etc., and a bit of mathematics, and just try to understand. And if you have questions, please bug me with your questions. Okay, so the only sources which we can detect at present is gravitational waves emitted from the merger of compact binaries. Okay, using the LIGO-Virgo detectors. Now, what actually LIGO-Virgo detectors see, they give us, like unlike optical detectors, where you actually see pretty images of the source or the planets or any star, here we don't see such things. We just observe some noisy data, okay, which looks like this in the time. It's a time series data, and we see a lot of wiggles and everything, and then hardly you can understand that if, oh, there is a signal inside it. So how do we process this data, and we understand that, okay, we have detected a signal, and we understand the source property. This is a bit challenging, and this is what I am going to talk in the next slide. So before understanding how we detect a gravitational wave signal, let's try to understand what is noise. Okay, so let's consider a time domain data, let's say a time series data from 0 to t. And if it is sampled at some discrete intervals where dt is t by n and n is the number of samples, we can consider n of t, which is noise, as a stochastic process, where each time whatever point we are getting is a random variable. Okay, sorry about that. Yes. So now if we assume that the noise is stationary Gaussian. Okay, now what do you mean by stationary Gaussian? Stationary means at any time of t, the probability, the PDF of the distribution, the probability density of the distribution doesn't change over time. So what does this mean? That the mean of the noise doesn't change over time. This is a major assumption which goes into the statistics and in understanding how we detect gravitational wave sources. Now, suppose the noise is Gaussian and stationary. This means that the mean of the this noise or the stochastic process is zero, and for the Gaussian noise, the probability distribution looks like this, where 1 by sigma is the deviation and mu is the mean, and this is how the PDF is defined for any Gaussian distribution. Now, if we take the autocorrelation of this particular noise, which is Gaussian in nature, and Fourier transform it, we get the power spectrum density, which is defined as in this way. Now, what do you understand by power spectrum density? It basically defines what is the power per unit time, per unit frequency in a frequency bin. This is what is power spectral density tells us. Now, suppose our spectral, this S, which is power spectral density, is constant, that basically correspond to white noise. Now, if you know what is white noise, I can give you an example. Suppose we are watching something on TV, and suddenly the cable disappears, and we see some this kind of noise with black and white dots coming on the screen. This is actually white noise look like. What does this mean? The white noise correspond to a same sort of power distributed over all frequency. This is what we see in the general case. But in LIGO or in our LIGO Virgo data, what we see that the noises actually have some power at different frequency bands, and this is what the sensitivity or the power spectrum density corresponds to for our LIGO detectors. Now, why do we need to know power spectrum density? This will come in next slide. Okay, so understanding gravitational wave and detecting them heavily depends on the match filtering process. Now, I'll explain how the match filtering process works, but before that, we'll understand what is hypothesis testing. Okay, so let's consider two hypotheses. Hypothesis 1, H naught, where we say that the gravitational wave is absent. In that case, our data will have only noise. Okay, and we are assuming that the noise is stationary, meaning the mean is not changing, and also it is Gaussian in nature, where the probability distribution is given by the probability distribution of the Gaussian function. Okay, so so let's consider the first hypothesis where the gravitational wave or the signal is absent, and second hypothesis H1, where we say that the signal is present in the data. So if it is present, the data output will be noise plus some signal, which is dependent on time and also the source parameters, where lambda is the parameter of gravitational wave signal. Okay. Now, how do we infer which hypothesis is correct? It depends on the Bayes theorem. Okay, so here I have attached the notes, and bear with me if there is something which you don't understand in terms of handwriting. Okay, so from the probability theory, we know that the two events, let's say A and B, the chances for occurring of A is A given B is given by probability of B into probability of B given A. Okay, and if we use this theorem to understand like what is the probability of event happening A, given that B is already happened, is given by this formula, which is called as Bayes theorem. Okay, so where we have likelihood, evidence, and prior defined in this way. Okay, Now we have already defined the two hypotheses H0 and H1. Let's consider the case of detecting gravitational waves. So let's assume that the H0 is corresponding to where the signal is absent and H1 is present. So if we please mute yourself. Yeah. I can hear some noise. Please mute yourself. Yes. Okay. So hypothesis testing continues. So we have the so let's consider the probability of detecting a gravitational wave in the data. It will be given by probability of H given H. This is the Bayes theorem which I was talking in the previous slide. And suppose if we want to talk about what is the probability of not detecting a signal, that will be given by P of H naught given S. Okay. Now, if we do some math over here, computation, we obtain the ratio of the probability of given the S given H1 and S given H2, this will form the likelihood ratio. And this basically defines the statistics which we use for claiming a detection. Now, going to the next slide. Okay, so here the same slide is being repeated. So here what we say is that the probability of detecting the probability of hypothesis H1 being correct given the data ratio, probability of H0, which is hypothesis 0, where signal is absent given the data, is basically dependent on this detection statistic into probability of hypothesis 1 given by probability of hypothesis 0. Okay, so this basically forms our detection criteria which we use for claiming a detection. Now, how do we know that the which hypothesis is correct will be clear in next section. Now we have calculated the probability of hypothesis 1 being correct over the other. But what do we how do we know that this is the correct one? Because the probability distribution for hypothesis H0 is this in the you can see over here at the bottom. And hypothesis 2 being correct has the probability distribution of this. So what we do, we put a bound. Let's say we put a bound as rho naught and rho star, and this we call as a threshold. And depending on the threshold, if any event which falls in to the right side of the threshold, we say that the signal is present. And if it is falling on the left side of the threshold, we say that the signal is absent. Okay, so this sort of forms the decision rule. And depending so the here I describe this particular formula, and this basically defines the optimal receiver, and this is also known as the Neymar Pearson statistics, which basically forms the match filter statistics. Okay, it will be more clear in the next slides. So this is just the repetition of what I said for the general scenario. But let's try talking in terms of interferometer data and gravitational wave. So we assume that the noise is stationary in the hypothesis test, where mean of the noise is 0, and the PSD is given by this way. And we want to compute the detection criteria, lambda over here, where the hypothesis 1 over hypothesis 2 likelihood ratio we compute. Okay, so if we go with the same recipe which we developed in the previous slides, what do we see that at any instant the probability density of detecting noise is given by n of t given in this form. So this is since we have said that the noise is stationary and Gaussian, so this noise is basically a Gaussian distribution. Okay. Now, if when the signal is not present, then my P of S given naught is basically a Gaussian distribution. But when the signal is present, there will be a contribution from the strain signal or the gravitational wave signal. And if we try to take the ratio of the two likelihoods, we will obtain our detection statistics given in this form. Okay, so for any gravitational wave amplitude A, the detection statistics boils down to this equation, which is nothing but the match filter statistics. Okay, now this is a bit complicated to understand, but let's move ahead. So we have developed this match filter statistics, which eventually forms the SNR of the signal. Okay, so now we know that the SNR is calculated in the following way, given in the previous slides, but how do we decide that the signal is detected or not? So that decision is based on what thresholds we keep on this likelihood ratio lambda. So let's say that the lambda is some value 8. If this if my this computation is basically greater than or equal to the detection statistics, we say that signal is present. But if it is less than the threshold, we say the signal is absent. Now, to visualize this in a simple language, what we understand is we have a signal. So here in the video, we can see we have the gravitational wave data and we have the signal, which is modeled, and we correlate the data with the signal, and we see the signal to noise ratio, which is lambda only. We calculated in the previous slide, and here we saw that wherever the signal matches the data completely, we see a signal to noise ratio peak. Okay, and this basically says that we have detected a signal. Now, because the data train is of months, and this basically correspond to millions of points, then basically we are generating too many triggers. We are generating too many signals over there. So what is happening? Any transient noise. So this is the data, and it has many transient noise. And any transient noise that satisfies the above condition, match filter statistics, and also passes this criteria, decision criteria, it basically give rise to a trigger. This is what in gravitational wave data analysis language we say that we have generated a trigger. Okay, now for if we want to understand how many triggers actually we generate for let's say 1 day of data or a couple of minutes of data. So if we say that there are 1 million points in the in 5 hours of data, then if we perform the match filter and we try to see this detection statistics, we basically end up generating 10 raised to power 5 number of triggers. This is huge if we are comparing with uh, 1 minute of data. Or yes, so this is the main challenging problem, that we end up producing too many triggers. But how do we claim that one of the trigger is actually our signal? So what we do for claiming our detection, we look for coincidences. What do you mean by coincidences? So suppose we have detected a signal in one of the detector, which is placed in Europe, Virgo. Okay, so that particular, if it is astrophysical in nature, in the sense it is produced by any binary black hole or binary neutron star event. So that particular signal should be seen in all the detectors. Okay, so this is what we call as looking for coincidences. So once we have generated all the triggers from each detector, we look for the coincident detection within the light travel time of 10 millisecond. So we assume that the time taken by light to travel from one detector to other is 10 millisecond. So within this time delay, we should be able to detect the same signals in both the detectors, and that's how we claim our detection. So here this is represented in the diagram plot over here, where we see that there are many noise events, and we see a peak appearing here and there. This is mostly glitch, but for detectors H and L, this is just a reference to Hanford detector, LIGO detector, and Virgo detector. So in all these three detectors, we see some sort of peak appearing. Now, the signal to noise ratio, if we try to filter it out, we see that the peak is appearing nearby. And if we compensate the time delay of 10 milliseconds between all the detectors, we say that there is a detection. And this is astrophysical in nature. Any other signal which appears, which is not coincident, they are considered and they are discarded as a glitch in the data. Okay. Now we have talked about understanding like how do we associate a signal to noise ratio for an event, but how do we know that this is actually significant event? Now, for understanding the significance of the detection, we assign a false alarm rate for that particular event. So what do we do over here? We false alarm is basically understanding the probability of false detections. So from this plot, what we can see, this is for the first event, which we had detected in 2050. We see that the background created by all the false events, or we can say that the triggers which can mimic like a signal, but actually it's not a signal, will form sort of this sort of background. These are the false events, and this is the one which is actually astrophysical in nature because this is found in all the two detectors, and the significance for this is estimated with respect to this background. Okay, this is how we assign the false alarm rate for the detection, and we say that we have detected any signal above some sigma. So here in this case, we assume that it's a 5 sigma detection. Okay, coming to the next slide. So we understand that the match filter process is in simple language, it's basically correlating our signal with the LIGO data. Okay, but correlating a signal with the model uh, depends on how well we model our signal. Okay, and signal model is one of the crucial thing for gravitational wave detection because it requires the information of in spiral merger and ring down phases of binary system. Okay, so in spiral, this basically can be modeled by simple equation, post-Newtonian approximation. I won't go into details how this approximation actually works, but the real part comes in modeling this part of the compact binary merger, which is merger and ring down, because this requires the knowledge of uh, numerical relativity, because the system goes very highly relativistic in this region, and we require a lot of computation and correct method to solve the Einstein's equation and everything, and then we basically end up in constructing this kind of waveform. So let's assume that we have got a perfect waveform for our signal, but what are the parameters it is depending on? So basically, the signal parameter depend on 15 parameters, which are 8 of them are intrinsic and 7 of them are extrinsic. The intrinsic parameters are basically they are the component masses of the source and their angular momentums, how they are spinning. And the extrinsic property is all the it comprises of all the uh, parameters in the detector plane. So how far the source is located, the luminosity distances are associated with it, the orbital inclination, at what time the merger happened, everything comprises of and it comes under extrinsic parameters. So considering all these parameters, we try to model our signal. This is one of the challenging part. Once we have modeled our signal, we pre-process our data. In what way? We get the strain data from the detector. We put a high pass and low pass filter to this particular data stream to remove all the artifacts. We wait with respect to the PSD, noise sensitivity, to get the actual power in the signal, and then we perform the match filter. So this is the overall view. So in a nutshell, what do? We have data obtained from interferometer. We have modeled waveform, which we model using numerical relativity and different approximations. We correlate these two data with the modeled waveform, and we get the correlation peak, which we associate with signal to noise ratio given in this way. And finally, we say that we have detected a signal. This is the whole procedure of detecting a signal, but there is a catch over here, because we don't know how the signal will look like in the space. We can't model with one or two waveforms, so we need a huge number of signals. So what do? We construct a bank of signals, model signals, with varying parameters. So for here in this case, I have shown how the masses will vary. M1 is the mass of the primary black hole, and M2 is the mass of the secondary black hole, and they are varying in certain fashion. And let's consider this particular template, and it has a mass of 150 and 65. So these many templates, which correspond to million of order, if we want to see the number. So we do the match filter over these many templates in order to claim a detection. Okay, so here the second part of my talk ends, and I know this is a bit difficult and complicated, but I'm ready to accept all the questions. So please go ahead. Is there any question? Please raise your hand.
Myself Vishwajit.
Okay.
Actually, I don't know how to frame this question, but it came to my mind. Like, we know that EM wave is generated due to the oscillation of charges,
Mm-hmm.
whereas gravitational waves are due to the disturbance in the curvature of space-time. So we know these two
Yes.
things are produced from a certain mass. So let's consider we are taking a pulsar as a mass object.
Mm-hmm.
So we are getting two signals simultaneously. One is the EM wave and also maybe the GW wave also. So
Mm-hmm.
how can we differentiate between them? Because GW wave is not an electromagnetic, because I don't know about much about this, but I have read in Google and all. So
Mm-hmm.
it is not an EM wave. So how can we differentiate? Because in LIGO, what we are trying to do is there is a laser and using the interference, and because there is a constant beam of light is going on with
Mm-hmm.
a certain frequency.
Mm-hmm.
So when this is getting impacted, the GW wave is getting impacted on that light, and we are getting some kind of interference pattern. And so how can we differentiate between these two waves? Like,
Okay. So,
because yeah.
answering to your question, see, if you're talking about pulsars or any other object, so the difference occurs in the frequency band which we observe. Okay, the gravitation wave emitted from the same source will be in certain frequency band, which is different from the EM counterpart. Okay,
Okay.
so the difference occurs in the frequency band. That's why we cannot see both of them in the same way. Does that answer your question?
Means if you are talking about frequency,
So okay,
spectrum, like EM
I
wave
don't have
already
an
has.
example, but I can go back to the old slide and
Mhm.
sorry, yes. So here in this plot, I showed that the frequency band, which the ground-based interferometer work, it's somewhere around 10 raised to power 2 to above. Okay, and if we see our LIGO in this plot, it's very clear. It goes from 20 hertz to some thousand hertz. Okay, now within this band, uh, we can detect gravitation wave sources. But if we compare the same source in EM band, that is quite different if we want to compare. So frequency is too high. So sorry, frequency is uh, too low in the case of gravitation wave, but it will be different in the case of EM sources.
Okay, so another thing is,
Yes.
so my second question will be like, whenever we are trying to, we have learned that using GW we can try to take from which source it is coming, right? So how
You're
do we do that? Like by GW waves, whatever we are receiving in our ground-based interferometers, how we see waveform waves? Yes.
Sorry, could you repeat because you were breaking in between? We couldn't hear.
Sorry. Hello.
Yes. Yes, please repeat the question.
Hi, am I audible?
Yes.
Okay. Yeah, the question is like whenever we're receiving any GW waves, so how can we detect the source from which part of or which object is it coming?
Yes, so we don't know the source location. That's the one of the problem which we face. So that's why what we do, we assume that the source is distributed in uniformly in the space, and we construct so many templates assuming that the sources are distributed in certain fashion. And depending on that, we try to do the match filter with all the uh, modeled sources, source waveforms, and we try to see whether we have picked this regime or that regime in the parameter space. So
Okay.
you are right that it is very difficult to probe the location of the source because we can't see them. But that's why we try to do match filter over millions of templates or the template waveforms to detect any signal.
Yeah, actually, I have read an article also. Even scientists are trying to implement, I guess it's a LISA actually, laser
Mm-hmm.
interference in space, I guess.
Mm-hmm.
So they are trying to detect. So now we have in our ground, and the next will be in the space.
Yes, yes.
So I
So that
hope that
that
will
will
bring the answers to our questions.
yes. No, so that will be looking for the sources which doesn't come under ground-based sensitivity. So that basically correspond to all supermassive black holes which are existing, but the gravitational wave emitted from those sources are too faint to detect to be detected from ground-based detectors. So that won't be solving the problem of localization, but it will be solving the problem of detecting more and more sources. Uh, does it answer?
Yeah.
Yeah.
Thank
Okay.
you. Thank you so much.
Yeah. I think I'm running. I have already taken too much time, so I will slightly rush through my next part of the talk, and this is the final part. Okay. So detecting gravitational wave signal. So again, I'll repeat this the same thing that we correlate data with the waveform, and we get the signal. And because we don't know what kind of sources out there, so we construct many sources, source waveforms, and we try to perform the match filter in order to detect them. Okay, but do we always detect astrophysical signal in the data? Answer is no, because there are oddities in the interferometer data. There are many sources which can act like astrophysical, but they are not. Like suppose, so they here I have listed many kind of sources which can give rise to a gravitational wave signal. This will look like a gravitational wave signal, but it won't be because these are emitted from ground-based perturbations which happen. Suppose air compression is not working, and then you see some sort of power which is coming in the gravitational wave data. So this basically pollutes our data, and do we have to worry? Well, not. We don't have to worry about this because there are sophisticated methods by which we remove all these non-astrophysical signals from the data uh, to detect the real astrophysical signals. Okay, so we have detected gravitational wave signals, but what do we understand about the source? So what do? We have detected from match filter algorithm what source we are looking at, But that is not enough because we still don't know what are the source properties and other things. So what do? We use Bayesian inference for detecting signal and for estimating its parameters. I won't go into the details of here. This sort of thing we try to do. I'll rush through the slide. Uh, so using Bayesian inference, where we know that already we have detected a signal, we try to estimate the parameters of the signal by this formalism, and this is very computationally costly. So there are sophisticated methods by which we try to speed up the calculation, and we estimate the parameters, which are 15 parameters, which I listed in the previous slide from this method. Okay, so these are the parameters which we had detected for all the 10 binary sources. This is the mass, and this is basically total mass, how it is changing. And there are other parameters also, the mass ratio of the binary system, and what are the chi effective, which is basically chi effective over here with respect to the mass ratio. So these sort of properties we try to analyze after we have detected a gravitational wave sources. Now, summarizing, we have detected previously the 10 binary black holes and one binary neutron star. And this was remarkable because this actually was also seen in other wave bands. We also see a optical EM counterpart, and later on we also saw emission in the radio band. And further analysis gave information about the galaxy it was residing to, and what do we get to know from this detection? We also got to know what are the heavy elements which were present, and which were emitted after this neutron star was merged. So this sort of information we got by one of the binary neutron star merger, which happened in 2017. Okay. Uh, Coming to the recent detections, so these are the two important ones. Why? Because we have detected last year a source which falls in a mass gap. Now, why mass gap? Because it's very hard to tell that whether the component mass is actually belonging to a neutron star or a black hole, where the primary one is actually a black hole. So this is an interesting discovery which we found. And another interesting discovery which we found recently was the intermediate mass black hole. Now, it's very hard to tell because whether the intermediate mass black hole exists or not. Why? Because most of the black holes, they originate from stellar evolution. So we have star, and then it ends up its life with by being a neutron star or black hole. But we don't understand these black holes which are of 100 solar mass and above. How do they form? So by detection of this particular gravitation wave event, it opened a new window where we study like how the hierarchical mergers of small black holes give rise to a bigger black hole. So this study is ongoing, and people are trying to understand, are there more sources like this in the nature, or they fall in this category. These are the recent detections, and these are pretty exciting. Now, what do we understand from the compact binary mergers? Okay, why CBCs are important? First of all, because first of all it helps in understanding what are the sources out there in the universe, and to understand their population and their formation channels and everything is something which we understand from gravitation waves emitted from compact binary mergers. It also helps in constraining the cosmology. This I won't go into details, but this is what we try to understand, how the H naught value changes. So here we have seen the constraint put by the Planck and supernova study, which is of this order, where in the case of gravitation wave study shows a huge variance over here. And this particularly will be shrinking over a few years when we will have more and more detections. And to constrain this particular plot, what we need to do is we need to build a larger number of detectors so that we can get more and more sources, and we need to develop faster search algorithms so that we don't miss any neutron star kind of detections. Okay, so future prospect, how LIGO India can help in improving the detection rate. So if you know uh, that the localization basically depends on uh, lambda by d, where lambda is the wavelength at which this our sources observe, and d is the baseline. So any detector placed over here and here, this forms a baseline. And from what kind of uh, localization it will be creating, that will be given by lambda by d. And if we have a network of detectors which is more in number, definitely our localization will improve. And this way we will be detecting more and more signals from as you can see from this estimate. Okay, so having a LIGO India will definitely going to improve our detection rate. This is what we hope for. And where do we stand? So uh, we have terrestrial interferometers. Soon or later in the future, we'll be having space-based interferometers, which will be detecting signals which last for a couple of hours. And these will be sources of extreme mass ratios and supermassive black holes, everything. And as we go down the sensitivity, we will be eventually detecting signals from the Big Bang. This is what we hope for, and this is our future where we want to understand. So coming back to the last slide, so we have heard sounds from compact binaries, but we are still yet to hear from other sources and backgrounds and Big Bang. So stay tuned. Thank you. Yes, question please.
I have two questions.
Yes.
The first one is once we detect a gravitational wave because of some event
Mhm.
in the past, so once we detect, then that is gone, or because the waves are being continuously created or transmitted in space and time, we can
Mhm.
detect that again and again.
Nice question. So in the case of compact binary mergers, as you can see, I let me go back to that video. Um, okay, I lost the video, I guess. Okay, here, I guess, yes. So in this video, what we see, the binary, these black holes in binary system, they are revolving around each other, and eventually they merge together. And so you will see they suddenly merged, and that's it. Like we don't see any signal from them. So there are sources, to answer your question, there are sources which are continuously emitting gravitational waves, for example rotating pulsars. Okay, but these sources, they emit gravitational wave in such a sensitivity which is not detected by our gravitational wave detectors. But if we consider the gravitational waves emitted from merger of any two binary black hole or neutron star, these are the sources which we can detect with our gravitational wave detectors.
So
So
that's exactly. So when you detected the peak, when you showed the background noise and
yes,
the peaks detected by all the four detectors in the around the planet.
yes.
So because the space time ripples are continuing, so we should detect that event again and again.
No. We detect. So that's what I was trying to say. So if the merger has happened, we detect the signal uh, one time. Okay. There are other things which I think it will be difficult to understand, but this is the scenario that the once the merger happened, because this is the time when the
Yeah.
signals is too strong and it falls under the sensitivity band of our detectors, so we
You
can
see,
detect them.
you ma'am, just see when you throw a throne in the water,
Yes,
the first wave hits the shore, so you
yes,
detect that. But
yes.
after that, the waves keep on coming and hitting the shore. So when
Yes.
what I say is, when you detect the first event,
Yes.
fine. After that, the space-time waves are keep on coming to us. We should be able to detect them as a attestation of the event.
Technically, we should be able to detect them, but they are fainter, so we don't detect actually, because the amplitude, if we try to see, the fast moving wave will be having a larger amplitude and more power, so that comes under the sensitivity of our detector, so we can detect them. But if we decrease our sensitivity to something much more higher, maybe we can detect the waves which are coming. Yeah.
Got it. And the second question is,
Yes.
the signal processing of acoustic waves. So generally we apply this convolution and deconvolution operator.
Yes.
So you do that in gravitational wave, because space time also is one of the medium. So do you put convolution and deconvolution operators?
We don't put, so here the detection of gravitation wave is purely statistical. So we don't do convolution, but we do correlation. If I come to the slide where we have data, okay, and we have a model signal, we correlate this data, and where we see wherever the correlation peaks, we say that we have detected a signal. Does that answer your question?
Yeah. Okay. Thank you.
Yeah. Okay. Is there any other question?
Yeah, so I had a question. Why
Yes.
exactly do we detect GWs? So how does it help us right now? Why do we do it? And what do we do it for?
Exactly. So this is the last slide which I was trying to understand, trying to explain over here. So we still don't know what all sources it can exist in our nature. Okay. So that is one of the thing which we would like to understand about. What is the distribution of binary black hole population or neutron star population, or if there are exotic sources like magnetars or you know intermediate mass black holes or supermassive black holes. So this sort of population distribution, which we don't know in other bands, we can also try to probe using gravitation wave. Okay. Now one more thing is that we just like other uh, yeah, so we can also try to understand the cosmology. Basically we can probe our universe in that way, so we can also understand the waves which are generated at the beginning of the universe through gravitational waves. So these are the problems which we try to address, and we try to understand whether it's possible or not. And just like in this particular slide, I explained that there is one of the recent detections which we saw about having the final black hole having a mass of above 100 solar mass. Now this sort of sources, they don't exist from the collapse of star. Okay, they can only form, or one of the possible way to form is they can smaller black holes, they can merge together and then they can form a bigger black hole. Now this sort of study we can pursue using gravitational wave as a tool, basically.
Thank you. So I wanted to ask one more thing.
Yes.
So there are also some neutrino studies related to GW events.
Mm-hmm.
So how do they help GW and vice versa? How do GWs help in neutrino detection as well?
Mm, I am not sure about this, but exactly how it helps. Um, yeah, um, I can answer this later question.
Okay, no problem.
Yeah. Is Is there any other question? Oh, I see. Sorry, I was not seeing the hands over here.
Like EM speed, does the medium decrease the speed of the GW?
Interesting question, actually. No, we do constrain speed of. No, no, it doesn't.
So they travel in the same speed in the vacuum, but one decreases with the medium depending on the type of medium. The other does not respond to the medium as far as the speed is concerned. Is that right?
So if I try to understand your question is whether the medium affects the speed of gravitational wave or not.
Like light is affected. Light is highest speed. C is highest in the vacuum, but the speed is drastically reduced depending on the medium. So whether the same phenomena happens to GW.
No, I don't think so. No.
Thank you. Thank you.
Good evening, ma'am. I have also a question. Hello.
I had a question.
Hello.
Yes, yes.
Yes, a gravitational wave have particle nature because have, you know, because every electromagnetic wave has
Sorry,
particle nature.
could you be just louder, little bit?
Gravitational wave have particle nature.
Okay, I see one
Gravitational
more
wave have
question.
particle nature. Hello.
No, I don't think anyone's asking.
No.
Is anyone asking a question?
I see so many questions on the chat actually, but I can't hear properly.
Yeah, he is.
Okay, let's actually tackle maybe a couple of questions from the chat. Advait, you're raising your hand. Do you have a question?
Yeah. I had a question.
Yeah, go ahead.
Yeah, it was a very wonderful session. Thank you for that. So I wanted to ask that as we can see the objects which are there today because of the light in our day-to-day life, but as light also has a properties like refraction. Similarly, gravity because of gravitational waves, we are now able to see the merging happening. So are like there any properties of gravitational waves that we are studying or we are ought to study that? Like light has something like refraction and reflection.
Yes, people are still studying and then they are trying to detect, but it's still like a tedious task to detect. But there exist phenomena where we try to understand the frequency modulation or refraction or these things from uh, of the gravitation wave. So suppose a small mass is kept, then suppose gravitational wave is traveling, and because of this mass kept in the between, it can hinder and it can deflect, the waves can deflect and it can modulate your signal. So maybe the source was looking different, but what you are seeing at the end, because of the interaction with the matter in between, it changes its property. So these sort of studies are still going on, and there are systems like a triple systems, like three black holes revolving around each other or other kind of systems. So there are studies which are going in this direction too.
Okay, thank you.
There is one question. So, can a gravitational wave be lensed? And if yes, how do we distinguish between a lensed gravitational wave and a non-lensed gravitational wave?
Okay, so gravitational wave can be lensed, yes, but then distinguishing is purely dependent on how we understand the source property. Okay, so as I mentioned in my slides that although we have detected a gravitational wave signal, that's not the end. We need to understand the source property. So a simple answer to this question is can be, so suppose we estimate the parameters of our gravitation wave source, okay, and it gives some luminosity distance, and it says that okay, this part of the sky it is coming from. If the luminosity distance and the sky patch is exactly the same, then we can say that okay, we are detecting lens signal, or the delay between the two signals we can estimate through parameter estimation and using Bayesian inference, and that's how we can claim the lensed gravitational wave sources. But it is difficult and people are still studying this. Does that answer question? I think it was Aditya Srivastava.
Yeah, I think his mic is not working.
Okay.
But there's one more recent question. Do gravitational waves exhibit wave-particle duality?
Mm, I'm not an expert in this field. Sorry.
Yeah, I think that's a pretty challenging question.
Yes.
Um, yeah, so I don't see anything else on the chat right now. Does anybody else have any other questions?
Yes, I do have one more question.
Okay.
So, for example, that the sources were like almost infinity, right? They're really far away. So, for example, if there was a hypothetically a chance that the sources were really close to us, then would the not that close, but close enough that we can detect it like really nicely? Is that like would it actually turn out to be like a really nice detection, or would it be the regular detection?
Okay, that depends on again detection of any source which is like very near or farther. It depends on how well we know the source model. Okay, so the match filter process uses the information of source properties, and that we put by hand. Okay, so if we are detecting any source which has like very loud in the sense it has a very high signal to noise ratio, and we are able to know the parameters very accurately, then we can say that it's a detection. And I think I mentioned in my talk that we only look for the coincident events. So that means any detection which we are seeing in one detector, that should be seen by all the detectors, given that the source is very near. Okay, so if all these conditions satisfy, then yes, we will be detecting a signal in the noisy band. So uh, to give more yeah, to explain this more, so we have this non-astrophysical signals which can arise due to any ground-based perturbations, maybe uh, any ripples which are caused by car moving, or earthquakes or anything, or maybe power fluctuation in one of the components of the detector. So these may look like a signal, but then if you try to if you want to distinguish between this and a real chirp signal, that will only depend on what kind of source model you are taking. So if this is accurate, and we will definitely look for a louder signal, and which will be astrophysical in nature. Does that answer your question?
Yeah, thank you. So I have another question.
Okay.
You use this waveform,
Yes.
and then you try to fit the data with the observational data, right?
Uh, no, we try to match our waveform, model waveform, with the observed data. Okay, fitting is different actually. So we match and we estimate this match filter SNR given in this fashion.
Okay. So would these waveforms would be the same? Uh, for example, that there was a specific waveform for black hole mergers. Would the waveform be the same for neutron star mergers?
No, no, no. So for neutron star, we have masses. Okay, maybe I should have put that slide how it is depending on source parameters, but I can explain that for neutron star, the masses are very small. Okay, so basically it spends a long time in spiral in the spiral phase. So if you want to compute the frequency time curve of any gravitational wave signal, which is given over here. For neutron star, this part of the waveform will be very long, as you can see from here in the plot. So the inspirer phase will be long, and the chirp, the merger phase will be different. So the waveforms will differ for different masses and different spins, and at different source location. So yes, we can say that our uh, waveform will differ for gravitational wave sources from binary black hole and binary neutron star uh, in this way. Is it okay?
Yeah, okay, it's okay. Thank you. It was a really wonderful talk. Thank you very much.
Yeah, I think I must have or should have warned you before that we have a really curious bunch of participants here. So that was, I think, a lot of questions. There are people asking me personally if you're going to be available later on, or perhaps on our Discord channel. We basically use something called a Discord server for keeping in touch. So I'll just send you an invite. If you can join, because I think a lot of people have more questions.
Yes,
But
yeah, I'll be happy to answer one of them. Yes.
okay, sure. Somebody is, I think you can go through the chat as well for a minute or two, because there is like almost a parallel discussion happening there.
Yeah, I missed all the discussion, but I can see the last question. Second last question is how deep learning is used in
Yeah.
gravitational. So, okay, one of the serious problem which we definitely will be running into in future is having more number of detections and having very large data set. So how do we handle these larger data set? We can use machine learning based algorithms to detect the signals. Okay, so deep learning is a part of machine learning, which is more convoluted, you can say. And we can use such algorithms to detect patterns in our data. And yeah, it can be basically used. And people are working on making machine learning based algorithms for detecting gravitational waves. So currently, there are projects which are dedicated to understanding, separating at least gravitational wave sources with the glitches which I talked. Okay, so those things can be handled very well using deep learning based algorithms. Uh, Pratmesh, yes. So does it answer your question? So does deep learning helps in decreasing noise? It doesn't help in decreasing noise. That depends, like what we are looking at. So deep learning can help in distinguishing between noise and real gravitational wave event, or maybe it can help in estimating parameters of gravitational waves. So it will only solve the problem of speeding up of detecting more and more sources. This is one of the advantage which we may see in future. What do you mean by quantum noise? Could you please elaborate on that? Okay, this part is something um, which I cannot explain right now, but I will definitely explain later, Aditya.
Okay, so I think, like I mentioned, we can continue the whole discussion. So I also wanted to just make a quick announcement since everyone is here. Our next session starts exactly in 20 minutes. So we have the basics of orbital mechanics and a little bit of rocket engineering by Karthik Tiwari at 8 o'clock sharp. So yeah, I think it would be fine to give a 15-20 minute break to everyone, and as well as Kanchan, because she's been talking for more than an hour and a half now. So thank you so much for joining us today. It was really insightful, and it was also more technical because, like I said, we had one introductory session for gravitational waves, but this was so much more in depth. And we're definitely looking forward to learning more from you. It would be wonderful if you become a part of our discussion forum as well. So thank you so much.
Thank you very much, and thanks for such nice questions. Yes.
Yeah. All right, and yeah, last reminder: if you guys are not part of the Discord server, please join. I'll just wait a minute. I'll put it on the chat box. The virtual campus. Okay, so the link is in the chat box, so you can just join the Discord server, and we'll continue the discussion over there. So yeah, we will see all of you in around 15 minutes. Those of you who want to remain on the call can do so, I guess, but just don't miss the next session, because that's going to be pretty interesting as well, and he has some cool simulations to show you. So yeah, we'll see you. Thank you so much, Kanchan, and I'll get back to you soon.
Thanks a lot. Bye.
Okay, bye.